Okay, we're ready for your questions. Hey,
I know we have a quiz tomorrow, and you said the quiz is based on definitions. So is the definitions from where, what? Hold on. I know you sent something about it. Let me quickly look at the email you sent.
okay, so the quiz three, let me go ahead and pin this, is on the definitions that we covered in class. On,
Okay, that was about disapproval and approval because we did a little bit of the disapproving. We took one example of disapproving a statement and the approving a statement, like if I'm not mistaken.
we had numerous examples. We proved two existential statements. We proved one universal statement, and we disproved a statement by proving its universal negation. So let's just if you want to know what's going to be on the quiz tomorrow, let's start with the definitions that you're going to for sure need. Shall we do that?
Okay, that's fine.
Yeah, well, it's not going to be on proofwriting the quiz tomorrow. It's just going to be on the definitions. So it might be something like this. I might say something like, fill in the blanks. So each definition is correct and complete. All right, so we're going to shoot for making sure that our definitions are both correct, but also complete. All right, so one, an integer n is even if, and then fill in the blank. An integer n is odd if, and then fill in the blank. Let's see, an integer p greater than or equal to 2 is prime if, and I think we'll need a couple of lines to fill that in. An integer n greater than or equal to, I know I might actually put a blank here. I could put a blank here and a blank here, is composite if, and then there are like three parts to that. And then didn't we have perfect square? Wasn't that the other one?
Yeah.
An integer n is a, did I call it x or did I call it n in the class notes? I think I called it n.
It's
A perfect square if then something happens. So these are the five definitions that we learned on day 9. Right? So shall we fill in the blanks to make these definitions correct and complete? Hello?
I'm still here.
Okay. So what does it take for an integer n to be even?
If it's divisible by two.
Well, we're going to be a little more specific because we want equations.
Okay.
So why don't you open the day 9 notes up?
No. If n is equals to 2k, for some integer k,
Yeah, we have a two-part definition. We have an equation where n equals 2 times k, and because k is a variable, we need to include information about what kind of number k is. So it's a two-part definition. See that?
yes,
And that's important because most definitions do have more than one part. Not always, but a lot of times. Okay, what about odd? What does it take for an integer to be odd?
um, odd is 2k plus 1.
What is 2k plus 1?
So that's gonna be, so it's gonna be, wait, if n is equals to 2k plus 1 for
Yes,
some int k.
yes.
So,
So again, it's a two-part definition, slightly different kind of equation for an odd integer, but still that extra information about the integer k. Does that make sense?
yes,
Great. Now an integer p greater than or equal to what? 2.
2.
Mhm. Is prime
If if p is divisible by 1 or itself.
and it's not just that it's divisible by 1 or itself, because every real number is divisible by 1 and itself, okay? And
Okay.
certainly every integer is divisible by 1 and itself. It's a little bit more than that. It's that the only divisors, the only positive, of course, 1 and p are going to be positive divisors, but the only positive divisors, this is an important word, of p are 1 and p itself. See what I mean? See the difference between saying that 1 and p divide p and saying the only numbers that divide p are 1 and p. Do I need to tell you a little bit more about the significance of this word only?
No, because we are trying to be more specific with it. That's been a little bit more specific.
That's right.
That there is nothing else that could only do it,
That's
that could
right.
do it,
That's right.
except a positive number, because we couldn't use we can't use a negative number to do that.
Yeah, we're not going to worry about the negative divisors. There are always negative divisors. For example, -1 divides any integer, okay? But we don't care
Okay.
about the negative divisors.
Okay.
We concern ourselves with the positive divisors. All right, how about composite?
N is greater than 2 if there exists an integer a and b such that n is equals to a times b and one greater than a greater than b. That I don't understand.
All right, we'll talk about that then. If there exists, so an integer n greater than or equal to 2 is composite if there exist integers a and b. Okay, so we have an existence statement that we have some integers a and b, and they have the property that, or such that, n is actually the product of a times b, so n can be factored into a times b, and a little bit more. 1 needs to be strictly less than a. And also, 1 needs to be strictly less than b. Let's take a look down here at an example to help understand what's going on with prime and composite. Find factorizations of each integer below that shows it is composite. Okay, so for example, if n is 18, okay, now we know we can factor 18 into 1 times 18, but that doesn't help us realize that 18 has what we call non-trivial divisors or factors. You see, we want to pick an A and a B where the A and the B are bigger than 1, and that means the other of A and B will be smaller than 18. So for example, 18, we could factor it as 2 times 9. Do you agree?
Yes.
And this is a non-trivial factorization because we're finding factors A and B, of course, they're integers, but they're each bigger than 1. 1 is less than 2, so 2 is greater than 1. 1 is less than 9. See, this is a non-trivial factorization. And what would be another way we could factor 18 to show that it's composite?
Um, it could be 9 and 2.
Could be 9 and 2, but there are 2 different numbers we could use for A and B completely. How about
Um,
3,
and
6? See that? Now, you don't
yes.
have to have 2 different ways to do it to prove that a number is composite, but this is helpful. Now, let me show you a non-solution. This will not help. So here's our caution. If we decided to factor 18 as equal to 1 times 18, this does not show. That 18 is composite. Does that make sense?
Yes.
Because our factors are the wrong kind of size. 1 is considered a trivial factor. We call it a trivial factor. 18 is the other trivial factor of 18 because every integer can always be factored as 1 times itself. So in general, n equals 1 times n does not help with this job of showing that n is composite. We have to pick factors where 1 is less than each of the factors. So here, 1 is less than 2, and 1 is less than 9. And that forces the other factor to be less than 18. So we get something that's strictly between 1 and n to show composite. Does that make sense?
Yeah.
Yeah, we gotta find numbers that are inside, in between the boundaries of the possible factors. 1 and n are always possible factors of an integer n, but those factors do not help us if we're trying to show that a particular integer n is actually composite. Okay. So how about we finish the last definition? An integer n is a perfect square if,
Sorry, I'm muted. If n is raised to the power of 2.
that's right. Well, it's not n, but if n equals some integer x raised to the power of 2. Now, okay, it is possible that x is n. For example, when n is 0, 0 is equal to 0 squared, and n equals 0 is a perfect square. Similarly, when n is 1, 1 is equal to 1 squared. 1 is a perfect square. But for perfect squares that are larger than 1, x and n will not have the same value. For example, when n is 4, what is x?
X is 2.
Exactly. So let's finish this definition. If n equals x squared for some integer x, we could continue our example 1 and put a part B. So let's say that we have n equals 256. How can we show that that is composite?
Um, we can factorize it.
Yeah, show me.
We could do the LCM and divide by 2. We could try dividing 256 by 2.
Sure. And actually, the LCM applies when we're looking at two integers and comparing them. Here we have a single integer and we're simply trying to factor it. But it is true when we play least common multiple games, we're looking at factorizations, but least common multiple has to do with a way of comparing at least two different numbers. We're looking for an either a greatest common divisor or least common multiple of two different numbers. But again, show n is composite. Here we're just keeping it real simple. So that's certainly one way to do it. Can you think of another way to factor 256 to show
Um,
that it's
I
composite,
have a question.
please?
So since we factored out 256 by 2 times 128, can't we factor out 128 any further?
Yeah. We can factor another 2 out of 128, right? We could factor this as 4 times 64, couldn't we?
Yes.
And in fact, one of the things that we're going to learn is called the standard factored form of an integer, where we tease out all the prime factors of an integer. We will do that in chapter 5. Right, so those are the definitions that you need to know. And I'm simply going to ask you to state the definitions, okay?
Okay.
Just as a way to make sure everybody's gotten at least that far. Other questions? Have you had a chance to look at the special homework number 5?
I did look at it, but I didn't really. I looked at it, but I didn't fully look at it. I didn't take my time to look at it.
I understand. Well, it's going to be
Um,
due on
Wednesday.
your Wednesday, right? So it'll be due Wednesday. So if you like, we could look at some of those.
Write on a state condition. So when we are writing a statement, write the statement as a conditional. Is that like giving it like P? Is that like, how do I say, P implies Q. Is
Correct.
that what you? Okay.
There's a good reason. That's a really good question. Why do we write a universal statement as a conditional statement when preparing for a proof or disproof, right? Now, why do we do that? Well, there's a real good reason for that. Let's look at an example. The product, this is example 2. The product of an even integer and any integer is always even. Okay, so let's just write the statement as a conditional introducing variables. So let's just warm up by doing one, and then we'll talk about why it's such a good idea. Write the statement as a conditional. We'll talk about why it's a good idea. All right. So this is talking about a product of an even integer and any integer at all. And it's saying that when we look at that kind of a product, that product is always even. So here we go. As an if-then, this is our good step 1. Well, how many variables are we going to need to discuss the objects in this particular statement?
We need two.
Yeah, we need 2. What do you want to call the even integer?
We could call it P.
Okay, I'm going to suppress the use of p because I don't know that it's prime. Could you pick a different letter?
Um, we could call it Y.
All right. And what shall we call the any integer?
X.
Great. So if y is an even integer and x is any integer, then what is supposed to happen according to this statement?
Is always even.
What is
The
what is
the
it?
the product is
Oh,
always even.
very nice. And how do we write the product using
Then it's gonna be Y times X is equals to even.
is even? I'll just use the words even. We'll get into the definition here in a minute, but for now, this is really nice. And the reason we like to do that is because we now can see the hypothesis. And the reason we want to get our eyeballs on the hypothesis of this if-then is because this is what we will assume. That's what we're going to have in our hand to work with. It's going to give us definitions and equations, whereas the conclusion that yx is even is what we wish to show. That's like the work that we have to do. And so, why do we do this? Well, because we want to see what the hypothesis is that we are going to assume. We want to know what work is cut out for us. What do we really have to do? And that's because in the direct proof method, when we want to prove just in general, for all x in D, if P of x, then Q of x. When we can see the P of x and we can see the conclusion Q of x, then we know exactly what to take for hypothesis or as hypothesis. The P of x, the hypothesis, is what we assume. We assume this. And that gives us, it gives us a place to start. And the Q of x, which is the conclusion, this is what we wish to show. So we know what we're shooting for. And that's for this proof method. We like to get our eyeballs on the hypothesis so that we know what to assume. We need to get our eyeballs on the conclusion so that we know what our work is. And in the direct proof method, the hypothesis is what we assume, and the conclusion is what we wish to show. There are other proof methods of universal statements. For example, you learned that there is an if-then statement that is logically equivalent to if P then Q. It's called the contrapositive. And because the contrapositive is logically equivalent to the original if P then Q, our next proof method will be proof by contrapositive or proof by contraposition, where we are going to look at the contrapositive and take its hypothesis as our assumption, and we will try to prove its conclusion. Then there will be another proof method called proof by contradiction of an if-then statement, in which we actually assume the negation of the statement is true and show that that leads to a mathematical absurdity called a contradiction. So we have three different proof methods to use to try to prove a universal statement, an if-then statement. Writing the if-then statement helps us decide what proof method is going to be the best proof method to use, and it helps us see exactly what we will be allowed to take as our hypothesis once we have chosen one of the proof methods at our disposal. And it will help us see what we're trying to do, what we're trying to conclude, what we wish to show once we have decided on a proof method. Okay? Would you like to see more on this particular example? For example, do you want to Shall we work through it?
Yes.
Right.
And also,
Mm-hmm.
does it also always have to be the direct proof method? Or do
No,
we? Okay.
no, we will have choices. Now, it turns out that
But how do we know which method to use?
that's a really good question. Um, one of the ways that we discover that the direct proof method, for example, is not going to be helpful is we lay it out as if we are going to prove by the direct proof method, and then we start working on the algebra using our hypothesis, P of x, and we find out that we can't get very far with our algebra using that proof method. We're going to see enough examples that I'm hoping that over the course of the next couple of weeks, you learn to recognize the kinds of statements that will lend themselves to the direct proof method and the kinds of statements that lend themselves to proof by contrapositive and the kinds of statements that lend themselves to proof by contrapositive. It turns out that while it's certainly not true that you can prove every statement using direct proof method, if you can prove a statement using proof by contrapositive or contraposition, you can also prove it by contradiction. Contraposition and contradiction are very similar logically, even though that may not be apparent from first glance. But that's something that I hope that you will just glean as you get more experience. Hi, John. So, yeah.
Howdy.
Okay. So, if we are going to try to prove that, what we've written here, if y is even and x is any integer, then yx is even because that's the way that we finally got that looking like. This will lend itself to the direct proof method very nicely. Let's just dive right in. Let's see if we can trust it. What should we assume using the direct proof method?
The hypothesis, namely.
Yep. And for the direct proof method, the hypothesis is our y is an even integer, or y is even, and x is any integer. So let's just assume it, and let's see how far we can get with it. Let's assume y is even, or you could say is an even integer. We know if we're saying it's even, we're saying it's an even integer. And x is any integer. So there's our hypothesis. That's the money that we are going to have in our hand momentarily. Now, what's our wish? What do we wish to show? Let's just remind ourselves that we always want to include thinking notes regardless of the proof method so that we know what it is we're heading for. So, Divine, do you see what it is we wish to show?
We wish to show the conclusion, which is yx is even.
Great. We wish to show xy or yx. I'll put it yx since you put y as an even number. It'll be a little prettier too with the algebra. We wish to show yx is even. Great. So now we are all set to actually push this proof through. We have something to work with. Now what? This is when you hear the voice, the hallowing voice speaking to us from the corner of the room. Look what we have to work with. Y is even. So what's the definition that's in play here?
One of an even number.
Y is even. Let's milk that for an equation, some information. So since Y is even, we have, or we know, or we see that, I'm going to skip a line because I like to neaten this up. Y equals 2 times what? What letter shall we use?
Let's say K.
K. For some K and Z. And actually, X being an integer, we're going to use that, but this is really all we get. We get that Y is equal to 2K, where K is an integer. Okay? Now, our wish points us to what we need to actually investigate. These wishes tell us what we need to look at. We need to look at YX. We want to say something smart about YX. Namely, we want to show that it's even. Okay, well, let's put YX out there and start talking about it. So notice YX. Well, how can we rewrite YX?
In the terms we just wrote it in. So we could say 2KX, for example.
2KX. And now we can just use associativity of multiplication and slide these parentheses over and group the K together with the X, but have the 2 hanging off the front. Let's take a breath there. Why would I do that? Why would I bother to explicitly pull the 2 out front? Well, what are we trying to prove about YX?
It's even.
Right, and we know in our definition of even that an even quantity needs to look like 2 times something, call it K, but it might be more involved than a single letter. And then we'll talk about that something. We'll talk about that quantity turning out to be an integer. So this is part 1 of the definition of even. Satisfied. See? Now we want to talk about this kx. In fact, we could write some more thinking notes. I probably should have done. We wish to show yx equals 2 times, I like m, 2 times m, where m is in z. Well, we got the first part done. We got yx looking like 2 times m. Here's our m, right? But now we need to talk about the second part of the definition, because the definition of even does have 2 parts. This integer, whatever letter we're using to represent it, needs in fact to be argued as being an integer. So why do we know kx is an integer? That's what we're calling our m here. Well, we talked about closure properties, that if we have 2 integers and we multiply them together, that product is always an integer. So we need to say that. And we're going to use the fact that k is an integer, and we're going to use the fact that x is an integer. We actually have money right here. It's kind of sneaky. It's up there. We didn't do much with it, but it's still there. So we used this here. But now we're going to use these 2 pieces of our hypothesis. Okay, well, since x is an integer and k is an integer, I'm switching from black to blue. I'm going to call it M. M equals KX is an integer because products of integers are integers. Or you could say the integers are closed under multiplication. You can say it either way you like. I think in the book in WebAssign, the author likes to say products of integers are integers. That's fine.
This is a sort of like stylistic question at this
Yeah.
point, because this seems like the kind of place where I would encounter this as like a real question for myself. Um, I guess, yeah. Like I say, I think maybe this is just a rhetorical question, but kind of want to see what your your feelings on it are, or what your preferences are personally. Um, Here, I would be inclined to use the sort of symbolic shorthand, like pretty aggressively. I would say something like since M, and then use the sort of like epsilon in, Z, kind of notation to talk about X and K. And I would say like M equals KX is in Z because, and then maybe there I would switch back to using English. Um, I guess, is there either a preference that you have or a kind of way that people typically will go about writing this type of thing in different contexts, or is it really
Well,
up to taste and
well,
not too sensitive to, kind of the topic?
I'm certainly not going to be very sensitive about it. At this stage of the game, some students aren't entirely comfortable with formal notation.
Hmm.
However, um, the level of play certainly dictates the amount of formality or that's considered okay. We
Hmm.
can quickly write this up using a much more formal notation, and either would be completely acceptable.
Hmm.
As long as a student is correctly using the notation, it's perfectly acceptable to use formal notation. It's a good question. And in fact, I probably would have preferred to get my wish a little bit further. The second incarnation of my wish probably would have been more helpful for me to have it here
Hmm.
before I even tried to satisfy, you know, part one of the definition of even.
Hmm.
But here, this is part two of the definition of even. Did I address your question?
Yeah, I think so. And just for transparency, I ask because I've noticed just kind of over time, I don't know, I pick up some book that I, think I'm going to be interested in, and sometimes I say, oh, this is like kind of obnoxious, and I this seems impenetrable because it's just a wall of symbols or something.
Well, and
And
that's
then
right.
on the other case, like there's another extreme, I guess, where it's like too prosy to kind of keep everything straight.
Right.
Um, and it's kind of a continually open question, and for me personally, like what the balance I want is, and maybe changes as time goes on.
So right now, I'm emulating what students are likely to see as they investigate some of these problems in WebAssign. EP is fairly
Hmm.
wordy in WebAssign, but not entirely. Like I said, we can rewrite this fairly quickly using a terser notation, but let's just go ahead and finish this so it's complete.
Hmm.
Thus, yx equals 2m. See, even though this was written here, it's in square brackets and is not compiling as part of the formal proof. That's one of the things we have to be careful with when we use square bracket documentation. It's not part of the proof proper. So thoughts and ideas that we are giving ourselves in this notation needs to be then made explicit in the formal body of the proof, where M is in Z, which makes YX even by definition of even. And that's, a full credit kind of situation. But certainly we could go back and look at this. And there is even a nice set notation for the even numbers. That's kind of fun. Why don't we explore that just because if we want to use set notation? And we will talk about this in class eventually. But it turns out Z is a set, and it is possible to perform arithmetic operations over a set, including multiplication or addition of each element by some value. So 2Z, well, let's just imagine, this literally means take each element of the integers and multiply it by 2. Okay?
Mm-hmm.
So what happens to
That's
negative
nice.
3? It is, isn't it? What happens to negative 3 when we multiply it by 2?
Well, becomes -6.
Of course. And we have -4 because 2 times -2 is -4. We have -2. We still have 0, of course. In fact, we can even drop a little bit of that. But this is the set of even integers. And this is standard notation for the set of even integers.
Hmm.
And then again, because we can play this game of performing an arithmetic operation to applied to each element of a set, we can shift this entire set by 1 to the right. So -6 plus 1, of course, becomes
-5.
yep.
Interesting. It's helpful to see this because my at least like my instinct would be to try to, I don't know, do some sort of like programming type way of expressing this, like use a, like a map function, something like this.
Well, this
Um,
is a function on,
mhm.
from a set to another set. So it is a function on a set of sets. I don't want to say the
Hmm.
set of sets because there is no the set of all sets. However, it's perfectly legitimate. And in fact, it's kind of pretty because then if you think of Z as this bag, where the evens and the odds live in there, it partitions Z into the evens and the odds with a really sweet little notation. And the beauty of this
Hmm.
notation is it will expand for divisors other than using the divisor 2. Here we're just looking at integers, we're dividing them by 2, and we're basically asking what's the remainder when we divide an integer by 2. Well, it'll either be 0 if, if the integer is even, or it'll be 1 if the integer is odd, the remainder. But the divisor could be 3 or 5 or any integer greater than or equal to 2. And you will get a nice pizza shape where you partition Z into these disjoint subsets based on remainder. And we're going to get into that. It's called congruence mod n. Here, n is 2. But the point is, we could now, use this nice notation to write this, rephrasing, and then we could let's just push it through. Is this okay with you, Divine? We're just going to rephrase example 2. We'll call
So
it,
what did you say?
we're just going to rephrase it using our
Okay.
new notation for evens. This set is the set of even integers. So we could just say what? If y is an element of the evens and x is an element of z, then yx is an element of 2z. Is that the only way that we could rephrase it? No, we could get even more terse. We could say y element of 2z and x element of z together imply yx is an element of 2z. These are, this is acceptable to answer your question, Jonathan.
Hmm. Yeah, this is nice.
Yeah, it's a little quicker,
Hmm.
right?
It's nice also to see them all kind of
compared.
yeah, compared. Exactly, yeah.
So assume y is in 2z and x is in z. We still have the same wish. We wish to show y at x is even, so is an element of 2z. And then we just go through, by definition of even. Or you might prefer here by definition of membership in 2z. I mean, I don't know how far you want to go with it.
Eh, uh-huh.
Yeah, but
Uh-huh. Uh-huh.
the point is you do have options. I'll leave that at that.
Mhm. Yeah, I mean this addresses a thing that I've found myself asking myself as I, I don't know, writing up some example or reading through the chapter. I'll ask myself like, I could go right, like, or define in some other line like QX to mean X is even or something like that, um, or some other thing.
Right,
But
right.
this gives me a nicer, sort of more satisfying way of doing it. Um, that um, lets me stay sort of more in the sort of the idiom of the domain, I guess, right? Like, um,
Ah,
if I pop in and out using sort of like black box single letter abstractions, like I just find like my working memory is not super great all the time if I'm tired or whatever. And so I don't always want to be doing that. I want to use like evocative things that remind me what I'm doing. Um, so I kind of like this notation that you just proposed for that reason.
I like it too, for exactly the same reason. And it reminds of sort of, you know, what is it that helps us classify an integer by parity, by evenness or oddness? It really is coming down to dividing by two and observing a remainder.
Mm, mhm.
And that has other applications and generalizations. Okay, so folks, it's 8:08 and I need to do some things. Does anybody have any burning last minute questions? Or I'm not gonna.
Um, so I wanted to ask, when is the scores for the test one gonna be available?
I'm working on grading test one now. I still have one student who needs to sit for the exam tomorrow. I'm hoping that will happen. But you should certainly get your exams back on Tuesday. The grades should be going up tomorrow at the latest.
Okay.
Okay. Yours,
And
yours is
mine?
actually, yours, I believe I have in my bag. Yeah, but I'm just trying to, yes, I did get, well, no, see, I'm trying to,
I took mine on Wednesday.
yeah, I can't remember if I wasn't on campus you took yours on Wednesday?
Yes, after the class on Wednesday.
No, it was Thursday. Was it Wednesday? It was Wednesday. Okay, I've got yours. That's right. I've got yours in the envelope. And if you like, I can try to float it to the top and let that be the next one I grade. Would you like me to do that for you?
Yes, because I know I have some questions on the um about the test, so I just want to get those questions answered once you are done grading.
Well, I need to reach out very, very aggressively one more time to a student who was supposed to take a makeup on Friday and reported to the room, but then didn't see the giant sized sign that said, please report to a different room because there were too many people to fit in that small room, claimed he didn't see the sign, and now he still hasn't taken the test. So I really do want to give you your test back tomorrow. So thank you for the
No, I could just come into the office to get if I could meet
please,
at the office
please do. I'll
to
be, yes,
to
please. We have
ask
an
like so
office
that the
hour.
question. Okay.
Sure. We have an office hour tomorrow after our class.
Oh,
Have an office hour from 3:30 to 5, okay?
is it on Zoom or
No,
in
it's in my
person?
office. It's in person, right upstairs on the third floor, faculty offices, okay?
I think I'll wait for Tuesday because I know you have an office hour on Zoom on Tuesday.
No, I don't. My office hour on Tuesday is also in person
Okay.
class. Um, if you would like to make an appointment for an office
Yes,
hour in
I
Zoom,
could do that.
then please ask for an appointment for like Wednesday evening. That could be possible. We could do a pop-up or
Okay.
just you and I. If you would like a private appointment, just make that clear in your email, okay?
Okay. Thank you so much.
You're very welcome. All right, so forgive me if
And I
well,
know you said you were going to upload the video from the office hours, but I didn't see the video.
yeah, uh-huh. Yeah, the video
I
didn't
only saw the
happen.
notes.
No, I will we have notes and I need to make a video and I'm not even going to get into why that didn't happen this weekend. It should happen soon.
Okay.
Sorry about that.
Thank you.
Yep.
Thanks a bunch, Dr. Good.
Hey, thanks for dropping in.
Enjoy your evening,
Okay,
and see you Tuesday.
thank you.